Hello everyone, welcome to my channel. This is Joe. Today we're going to learn how to design some simple combinational logic circuits. Since we already learned the necessary knowledge and the tools, we are already able to design some of the circuit, very practical circuit. Before we talk that there are two major types of logic circuit. One is called a combinational logic circuit. This is the circuit whose output is only the function of current input. The other type is called a sequential circuit. Its output is not just the combination of current input, but also it's a function of its previous output states. So that's called a sequential. But today we only focus on combinational circuit. Here is a list of the steps we usually use to design a combinational logic circuit. First, we always need to understand our project, like what we are going to make, what's the main function of it, right? Then we have to define the input and output variables. And also, we need to know how will the output be changed as a function of the input. And another important thing is that we need to understand what are the active levels of the input and output variables. About active levels, we will talk shortly. Okay. And also, if there's any special requirement, we should consider we need to know what are they and what we can do to realize them. So after you have a clear picture of the project, then the most important job is to translate those information into a truth table. Once we have a truth table, we can use the column map to get the simplified Boolean functions. Then we can generate the logic diagram based on the functions. And also we can do some verification of our design. Before we work on a real project, let's first talk about the active levels. So in a digital system, the active level simply means the logic level that activates the system. Okay, so basically you can think this is the voltage level that make the circuit work with normal function. Okay, and theoretically, any digital system can be designed either to be active high or active low. To give you a better idea of this, let's say we wanted to control a lamp. So first, let's design that when the lamp is on, that's equivalent to logic 1. If it's off, it's equivalent to be logic 0. Okay, so in order to turn on this lamp, we have two ways to collect the lamp. If you know a little bit about circuit, we know that to turn on the lamp, we need a voltage difference between the two sides of the lamp. So the first way of collecting the lamp is that I collect one side of the lamp to the ground. Then for the other side, I collect to a voltage source. Okay, so forming a circuit like this. In order to turn on this lamp, we need a voltage drop, so which means I need to put a higher voltage here. So we think we put a logic 1 here. So the logic 1, if we have a logic 1 here, then this lamp will be on. However, if we put a logic 0 or low, then the lamp would be off. So in this case, a high voltage causes the lamp to be on to work, right? So we call this is active high logic. So on the other side, we have the same circuit, similar circuit, maybe I try it differently. So I still have the nap here, but this time we fix the other side of the nap to a high voltage. So this is equal to logic high. Then we collect the lower end of the nap to our voltage source. Now this time, in order to turn on this nap, we actually need to input a logic low voltage or zero, logic zero. So we have a voltage difference. So this will be up. So in this case, a logic low turn on the lamp, make it work. So we call this active low logic. So this idea is very important because throughout this course we are using this concept a lot. Okay, let's look at our first design project. So the alerting and alarming system. So here is the description. Say we have in the factory we have a chemical tank which is used to store some maybe dangerous chemicals. So in many cases we need to monitor the fluid inside the tank to make sure no accident happens. Usually what we do is we collect some sensors to it. In this case we have 3 sensors that attach to this tank. The first is a level sensor. This is to monitor the liquid level in the tank. And if the liquid level is too high, it will give a warning. Okay. The second sensor is a pressure sensor. So it monitors the pressure inside, like the air pressure inside the tank. If the pressure is too high, get higher than a certain level, this sensor will also give an alarm. The last one is a temperature sensor. This is to monitor the temperature inside the tank. If the temperature is too high, or higher than a certain level, it also gives an alert or alarm. Okay, so I think you can picture this, right? We got a tank, we got some sensor attached to it. This sensor will give signals if something wrong. Okay, and more specifically, here we define that those sensors, when they detect something unusual, they will give out a logic high signal. So they will give a logic 1 out. Okay, now we have this system. Where the 3 sensors are collected. So right now we just call it a safety system, but fundamentally it's a control system. So this system will be used to control 3 nights, and all the nights are active high. If you remember what we just talked about, active high, right? Means logical 1 will turn on those nights, logical 0 will turn them off. Okay, a green light designated as OK state, indicating that the system is functioning normally. Normally means none or only one sensor generates a logic high. So basically it says if one sensor detects some unusual thing happening in the tank, it's okay. So it's not a big deal. And a yellow light called alert illuminates if 2 or more of the sensor generate logic high. But say now if 2 sensors detect abnormal states inside the tank, then we probably need to start being alerted, right? So the yellow light will be on. Finally, the red light, designated as danger, illuminates when all 3 sensors output logic high. Now, this is the most critical condition. all the sensors give a warning, something going wrong, so it's dangerous. Then the red light tells you that it's dangerous. Okay, so the question, can you design the safety system, realize this function? So here we will start the design cycle. Remember, the step one is that we need to understand the question properly. Okay, so for this case, we can actually use a drawing to picture the system so we have better understanding. So say we have a tank. There are some chemical inside, and they are dangerous chemicals, so we better monitor the status of it. And we have three sensors attached to it. We have the level sensor, pressure sensor, and temperature sensor. And these three sensors is connected to a safety system. And this safety system is used to control three lamps, and all the lamps are active high, which means a logical 1 on this line will turn the lamp, which also means the other end of the lamps are connected to ground. And we have a green light, we have a yellow light, and a red light, right? So you probably already see our goal is to define this guy here. Then we have to figure out what's the input for this circuit. Very clear now, right? It's this the output of the sensors L, P, and T, and they are active high. Basically, when the sensors work, they will give out active high on the slides. If nothing wrong in the tank, it gives 0. And what's the output? The output is actually the wire collect to control the three lights. Right? The output is not actually the three lamps. It's the signal to control those lamps. But here we can still use the same letter to represent those signal lines. So output would be the signal line for green light, yellow light, and the red light. And remember, they are also active high. You must put the active level here, so you know you need to put a 0 or 1 in the truth table later. Okay, basically we have the input and output now. Then the next thing is to figure out the relation between the input and output. So how the output changed. So based on the description in the previous slide. So let's try to fill out this simple table to clear things out. So basically the impression we have now is that the output, those three lights, they are on or off. Kind of depends on how many sensors give signals, right? Give the one signal. So if there's no sensor gives high signal, which means this is the in OK state. In OK state, the green light should be on. Now, what? So right now, let's not put 1, 0 yet. So I just put green light on. So these two will be off. If one of the sensors gives high signal, if you recall the description, it's still calculated OK. So still green light on, the other two off. If two sensors gives high signal, which means there's something wrong, you need to be aware, but not very critical. So this is alert. In this case, we know yellow light will be on, the red and green will be off. If all the sensors gives out signals, which means it's danger, right? In this case, green would be off, definitely. The red will be on, but the yellow is will be on when 2 or more sensors give signal. So in this case, the yellow will also be on. So once you figure out this, which light is on and off at which condition, then we are ready to translate this into a truth table. So because we have 3 inputs here for that circuit, so from what we learned before, then there will be 8, right? 0, 1, 2, 3, 4, 5, 6, 7. So either min term or max term. There are 8 of them, 8 possible combinations, and the output is G, Y, and R. Now let's redo this. So 0, 0, 0 basically means the 3 sensors gives no reports no issue, right? No issue in the tank. This is the OK state, which means the green light will be on. Because green light is active high, so we need to put 1 means it's on. Then 0 for these two means they are off. 0, 0, 1. Only the temperature sensor gives out high signal, which means the system is still in OK state. So we still have this. 0, 1, 0, only one sensor gives signal, high signal, so it's still OK. Now we have 2 sensors gives out high signal, which means it's in alert state. In alert state, yellow light should be on, the other 2 should be off. 1, 0, 0. Now we know it should be green light should be on, the other 2 should be off. 1, 0, 1, yellow light on, others off. 1, 1, 0, yellow light on, others off. 1, 1, 1, the yellow light and the red light are both on, but green light is off. Right? So once we understand the system we are designing, we can generate the truth table. The next thing is, because we have 3 output here, so we need a Boolean expression for each of them. So totally we need 3 Boolean expression, which also means we need 3 column maps, 3 input column maps in this case. So the first column map is to generate the function for G, or the green light. First, we need to translate this. If you remember how to translate, 0, 1, 2, 3. Remember the number for the squares? Yeah, just be careful. 2 and 3, 7 and 6 we need to change the place, because that's how the column map works, if you remember. So if this is L, this is PT, so we can write down, translate the green light, the truth table for green light is 1, 1, 1, 0, 1, 0, 0, 0. Okay, remember how to group this. So we look at this one, we can group these 2 together. When we look at this one, we can find that these 2 are labeled, so we can group these 2 together. And also for this one, we can group these 2 together. Then we can write the expression for green light, which is equal to, for this group, L is taken out, so we have P and T both equal to 0, so write P prime, T prime. Or if we check this one, L is there, which is L prime, T is gone, so we have P here and P prime, and the last group here, L still there, and the P should be gone, so we have T there, so T prime. So we got a Boolean expression for green light. Similarly, let's handle the yellow light. So still LPT for yellow. Let's translate it. Maybe still use red. So 0, 0, 0, 1, 0, 1, 1, 1. So 0, 1, 1, 1. So how to group this? Similar thing, we can group this 2 we can group these two, and we can group these two. So the expression for yellow light equal to, check this group first, L, P is out, but we have T, LT, or L out, have PT, or LP. Okay. Finally, let's figure out the red light. The truth table for red light is this column. It's pretty simple. Everything is 0 except the last one. Okay, so R should equal to, there's nothing to simplify, so R just equal to LPT, where everything is wrong. So now we got the expression for the three outputs. Now the final step is to figure out the logic diagram, so we can make this circuit, the physical circuit. So let me rewrite the expression here. So green light equal to P prime T prime L prime P prime L prime T prime, and the yellow light equal to PT or LP or LT, and the red light equal to LPT. So how to draw the logic diagram? There's an organized way to do this. So what we do is we put our input signals. So we have L, P, T. We draw a long line of them. And also we need to generate their complement form. So basically you just pass the original signal to a NOT gate, right? And then this line stands for L prime. You can also do this for P. So here we got P prime. For T, we got T prime. Okay, so the first function, green, so let's use the green. So it's P prime, T prime. So you just find the corresponding line. This is P prime, which means we are collecting this two together using an AND gate, right? And L prime, P prime. And L prime, T prime. Right, so this function, this is SOP. So we have product term first, then we have the sum term using OR gate, 3-input OR gate. So this circuit will realize the green light. And for yellow light, PT, LP, and the LT. Oh, sorry, PT, this is LT, so we need LP. For the red light, we have L, P, T, just one gate. So that's the logic diagram. If you fabricate this whole thing into a chip, basically this is our safety system. And then another 3 input, 3 output. So to this step, we have finished the design for the combinational logic. And this is a very typical example for designing a combinational logic circuit. And if you want more function or you want to change some function of it, you can also do the variation. For example, let's change the project a little bit and see if we can still do it. So we still have the tank and the 3 sensors, okay? But now the 3 lights is active now, which means the 3 lights, the other end is connected to a high voltage, okay, or logic high, which means we need the input at 0 to turn them on, okay. And now their operation is also changed. A green light designated OK indicates the system is functioning normally. Normally now become no sensor generate a logic low. This is different than before, right? No, which means this system has to be no flow when it's in OK state. But if there is one sensor that generates the logic low, okay, so now the sensors are also being defined as active low, which means if something wrong in the tank, the sensor will give out 0, not 1 anymore. If nothing wrong, it gives out 1. Okay, so opposite than before. Both the light and the sensor is opposite compared to the previous version. Okay, and we have a red light designated as danger, illuminates when 2 of the sensor output logic low. So 2 sensors detect abnormal status inside the tank. Finally, all 3 lights are if all sensor generates logic low, which means everything is on in the tank, then all lights are designated as deadening. So you can see that in this case, we have four conditions for the tank, 1 more condition than before, right? But we can still figure out the truth table because it's still, this system still has only 3 input and 3 output. So we still have same thing here, G, Y, and R, but the truth table is totally changed, right? So 0, 0, 0 here means what? Because the sensor is active no now, 0, 0, 0 actually means everything is wrong inside the system. When everything is wrong, that's deadening, and all sensors generate no, and so all lights should be on. So green should be on, but remember 0 is on now. Yellow also need to be on. Red also need to be on. Then 0, 0, 1, which means 2 sensors detect something. The other sensor is okay. In this case, which light will be on? 2 of the sensor output logic no, which means danger. So R light should be on. So R should be on. Then the other 2 should be off. Then 0, 1, 0, only 1 sensor, still 2 sensors gives out low signal, which means danger. So R should be on, the other 2 should be off. 0, 1, 1. So only 1 sensor gives out low signal, which means alert state. In alert state, yellow light should be on, the other lights should be off. The next 1, 0, 0, so 2 sensor detects things. So yellow light should be on, the other 2 should be off. And oh, sorry, not yellow light. So I have 2 sensors give out abnormal states, which means this is danger. So R should be on, these 2 should be off. 1, 0, 1, this is alert. so this will be on, this 2 will be off. 1 1 0, danger, so 0 1 1. 1 1 1, nothing is wrong, so nothing will be on, so you get 1 1 1. Okay, so in this case we still have 3 outputs, so we still need 3 column maps to do the simplification. But to save some time, I just show you one here. Let's try yellow. You can do the other 2 by yourself. Okay, so yellow, still we have LPT, but the truth table for yellow changes, right? So now it's 0 1 1 0 1 0 1 1. Okay, so we need to simplify this. So we can do that. We can do that. And then we can do that. For this one, no choice, just group by itself. So we have 4 groups here. So actually y should equal to this one here, which is L prime P prime T. And then this group is L P. This group is PT prime. And then this group is L T prime. So that's how you work on it. So no matter how you want to format or put your system, you can do it now. Okay, and you can even try add another input or output and try it again. Now the second project I want to talk about is the control circuit for the LED volume bar display system. So this picture here is showing you the diagram for like real karaoke system. So say in a karaoke system we have a music source, and this music source is going through an amplifier because we want a bigger sound coming out from the speaker, right? So it's need to go to an amplifier, and also we need a microphone to input our voice, and this voice will be mixed with the music source. Okay, so everything is going through the AD converter because all the voice is analog signal, so they need to be converted to digital signal, then be mixed and processed in the microcontroller. Also, the volume control is also happens here. Okay, and if there kind of video, we can also have LCD display to show the video, and we have some memories to store some information if needed. So after everything is processed, it be sent to a DA converter. So now we will convert digital signal to analog signal again, and the analog signal will go through a speaker. Then we hear our sound be mixed with the music source. Okay, so this is kind of sophisticated system, but here we only do a very little part, which is the volume bar control. Okay, so if you saw the volume bar on the music player system or karaoke system or anywhere, right, it looks like they write graph here. So when the when the volume changes, there are different lights on and off, right? Now you need the red lights, and by the way, all the lights are LEDs, light emitting diode. So and they have different colors. You need the red color means high volume, green color means low volume, yellow is in the middle. Okay, so how this LED works, be controlled. So we will do that, but we will use a simplified example. So say we have a column of LED. Yeah, something like that. We have column LED. We don't care about the color here yet. We just talk about when they should be on and when they should be off. Okay, so we have 7 of them. Say, sorry, let's start over. So basically, we wanted to have a control circuit to control the volumes. And here we have, say we have 8 different volume level. So from 0 to 7, 7 would be the maximum. Okay. To represent those 8 volume levels, actually we need only 7 LED. Why it's 7? Because for 0 value, we don't want anything on. Okay. Then the 7 LED can stand for 7 different non-zero volumes plus nothing on, so we have 8 levels. Okay, so that's why we only need 7. So how to design such a logic circuit? Again, the first step is to understand this problem clearly. So here, this is a diagram shows what will happen when the volume change to each state. So the first column shows that there are 7 LEDs. If all of them are off, we stand to the mute state, like no sound, the lowest level, right? If the first LED is on, we got the first volume level. Then the bottom 2 LED on, mean level 2. Bottom 3 on, level 3, 4, 5, 6, 7. You can understand this concept. Yeah, but since we have 8 different states, so how many control line we need? If we think about what we learned in the second lecture, right? The binary number, the combination. To reach 8 states, we need 3 control lines. Because 2 to the power of 3 equal to 8. Right? So now we have the idea. How many input for this volume control? Volume bar control. So we have 3 inputs. Here we name them D2, D1, and D0. How many output we have? Actually, we need how many? 8 or 7? We only need 7, right? So that's LED. You can from 1 to 7, or you can put like 0 to 6. That matter. Okay, but we only need 7 output. Okay. Let's put everything to truth table. So here I use L0, L1, L2. Actually, so we don't need this column. Actually, we only need 7. So L0 stands for the bottom LED. So when will be on? Or let's do the horizontally. So if the input is 0, 0, 0, which means the lowest volume level, and also assume all LED are active high, then what will happen? Nothing will be on, so everything will be 0. Then we tune the volume to the first level. So LED 0 will be on, right? The others will still be off. Then to the second level, so this decimal 2, right? Then the bottom 2 LED will be on. Now level 3, the bottom 3 will be on. Level 4, the bottom 4 will be on. Level 5 and the level 6 and the level 7, right? So for level 7, the maximum volume every light should be on. Now since we have 7 output, so we need 7 karnaugh maps. So let's translate them first. So L0 for this column, we have 0, 1, 1, 1, 1, 1, 1. For L1, we have 0, 0, 1, 1, 1, 1. For L2, 0, 0, 0, 1, 1, 1. L3, 0, 0, 0, 0, 1, 1, 1, 1. 0, 0, 0, 0, 0, 1, 1, 1. 0, 0. This is L5, so we got 6 zeros. Finally, we got 7 zeros. Okay, then next step to group them. But there's, if you check L0, you can go to group as 1. But what's the other option? Instead of POS, we can do SOP, and there's only one group. This is much easier to do, right? So we can directly write L0 equal to, now this is POS. Remember, POS means we need to write the simplified term into sum terms. So this will be A or B or C, because we are grouping 0 here. Similarly, this is much easier than grouping ones. So we can write L1 equal to, A is not changing, so we put A, and C is changing, so just B, A or B. Yeah, if you forget how to do the POS using column map, please go back to lecture 6, okay, the topic 6. For the other one, also it's easier to do POS, and we have only 2 groups. So L2 equal to, for this one we have A or B, and for this group we have A or C. And then now this is doesn't matter, use group 0, 1, let's try 1. L3 should equal to A, just A. And here now it's easier to group 1, so we do SOP. So L4 equal to, for this one we got A, C. For this group we got A, B. And here we have L5 equal to A, B. Last one, no simplification, so L6 equal to A, B, C. So that's the Boolean expression for all the outputs. Finally, is to generate the logic diagram. And because it's a matter of time, so I don't want to show you everything. I just again give you an example. So we have 3 input here also, which is A, B, and C. So here I just want to draw L2 to give you an idea, because this is POS. So I showed you SOP before in the first project. So I just give you one example for POS, you know what to do. So A or B, similar thing. You just collect the wire out. This dot means these 2 wires are collected. So because A or B is all function, so you need to draw the all function here. And we need an A or C. Or C. And their result will be added together. So the second level is an AND gate, which is L2. I believe you can do the others by yourself, so I will skip them here. Okay, now you see with those basic skills and tools, you already be able to design a lot of combinational logic circuit, even by hand. For system with more than 4 variables, we said you probably want to use a computer system to help you solve the column maps. Okay, but you can still do the design manually. Okay, so that's today. If you think my video is useful, please help like, share, and subscribe. See you next time. Bye.